Okay, this should... Oops, I'm in trouble balancing my phone here. Alright, there we go. There we go. Yeah, this will hopefully be the last one of these. So I've got 18. So here we go. And it's bounded by y equals x plus 1 and y equals x squared minus 2x plus 3. And that's all we're given. So, having nothing else to go on, well, okay, maybe I should say for first things first. These are both solved for y, so probably when I set this up, I'm going to do y is going to go on the inside, and the limits of integration for y are going to be this and this. Now I'm going to have to think about something, and I'll get to this. I'm going to have to think about which one of these is the bottom limit and which one of them is the top. It depends which number is bigger, but we'll get to that in just a moment. But as of right now, what I have in my head is that y is going to go on the inside, so it's going to go dy and then dx, and my limits of integration are going to be this and this in some order. And then x is going to be on the outside, and the limits of integration for x just have to be numbers. They can't depend on any variable, and I'm going to have to figure out what those numbers are, and I'm probably going to do that by setting these two things equal to each other. So where do they meet? They meet where this equals this. So 0 equals x squared minus 3x plus 2. And look at how nice I was. That factors down into x equals 1 and 2. Yeah. Okay. And yes, I'm getting closer to being ready to set this up. Let me actually address the question I started talking about just a minute ago, which is here. As I said, I'm going to go dy dx. X is going to go from 1 into 2, and y is going to, the limits of integration for y are going to be these two things, but I was talking about how I'm not sure which one to put on the top and which one to put on the bottom. It's really just a question of which one of these numbers is bigger for the values of x that we're interested in. And let me make this decision in the easiest way I can. I'm just going to draw a little graph. So I don't need to draw a great picture for this. This is a line. I can draw that. Here's an accurate picture of that. This one's a parabola opening up because it's a positive x squared, and I know it crosses at x equals 2 and x equals 1. So it's going to say cross here and here. So I'm not going to insist on drawing a great picture. But the point is, and all I'm interested in, this picture isn't really necessary. It's just my way of figuring out. The only thing I'm interested in for my purposes right now is which one of these graphs is on top of the other one for values of x between 1 and 2. And the answer is, because this is a straight line and the other one's a parabola opening up, it looks this way. The parabola is coming from above, it's dipping underneath the line and then coming back up. So in between values of x between 1 and 2, the line is on top, the parabola is underneath. So the parabola is going to go, oops, parabola goes here, x squared minus 2x plus 3. The line goes here. There we go. So now this is set up. It is just a matter of evaluating it. So I work my way from the inside out. So this is the antiderivative with respect to y, so that's just, I'm going to stick a y on there. So it's like that. So this is okay. Now bear with me. I'm going to plug in x plus 1 for y. But if you will, well, you're not actually here, so you're not going to be able to stop me. I'm going to go ahead and multiply this out as I go. So y is x plus 1, and I'm multiplying that by x. That turns into x squared plus x. It's not that bad. I just, when I plug in y, I have to multiply everything by x. So here I go for the next part. I'm going to multiply everything by x. So this turns into x cubed minus 2x squared plus 3x. Right? Okay, a little bit of math to do here. Let me write my x cubed first, and then let me take care of all my x squareds. I've got a positive x squared and then a positive 2x squared, so plus 3x squared. And then I've got an x minus 3x, so minus 2x. Okay. So I've got that plus x cubed minus x squared, 1 to 2. So 2 to the 4th is 16, so this is going to be a negative 4 plus 8 minus 4. And then I'm going to subtract what I get from plugging in 1 everywhere. I get that. And this is all just 0. And then this cancels this. The only thing that's still there is 1/4. Great. Next thing is, these are the round 2 problems. Okay. I've got this triple integral. S is the unit sphere. X squared plus y squared plus z squared less than or equal to 1. And the recommendation is to convert this to spherical coordinates. And I plan to tell you this part on the test. Whenever you convert a double integral or a triple integral to another system of variables, and the most common thing to do is to convert to either polar or spherical. Polar is 2 dimensions, spherical is 3. Whenever you do that, you need to convert not just the function on the inside, but you need to multiply that by an extra factor, which is the absolute value of the determinant of the Jacobian. And for spherical coordinates, that's always rho squared sine phi, and I plan to tell you that. Okay, here we go. I'm not even going to bother setting this triple integral up fully in terms of x, y, and z, meaning like putting the limits of integration for x and y and z, because I know I'm just going to convert it. It would be pointless for me to do that. But I'm going to talk about it anyway. I could solve this for z like get the x and the y over and take the square root. So z is like, we've seen this a million times. It's these ugly like square root of 1 minus x squared minus y squared. Like I could put that as my limits of integration for z, and there would be a negative square root and a positive square root, and then y would go from a similar like negative square root to a positive square root. I'm just describing in words what it would look like if I fully set this triple integral up for the variables x, y, and z. But I'm not really going to do that. So here's what I am going to do. First of all, okay. Rho squared is x squared plus y squared plus z squared. And when I was fumbling for just a second there, I was thinking to myself, maybe I should give you all the formulas to convert to spherical. We don't need them right now. I just need this one because this is rho squared. I plan to, when we convert to spherical on the final, I'll give you the formulas for converting. It's like x equals rho sine phi cosine theta, and then y equals, yeah, I forget, to be honest. But I'll put it on the final for you. For right now, all we need is this one, though. Okay, moving on. Let me do my triple integral. We are doing the entire sphere. This is a very friendly region to represent in spherical coordinates, hence the name. And my limits of integration for rho and theta and phi, they're all just going to be numbers. None of them are going to depend on other variables. So it does not matter at all whether I go d rho, d theta, d phi, or whatever. I'll go like this. My limits of integration for rho are going to be 0 to 1 because this is a sphere of radius 1. And also, we're not going to do negative values of rho for spherical coordinates. So in the absence of any other sensical lower limit, you would just use 0 for the lower limit. So that's rho. Limits for phi, if you recall, phi is like this angle. So when phi is 0, we're pointing straight up. When phi is pi, we're pointing straight down, and that's the full range of phi. And we're doing the entire sphere, so phi is just going to go from 0 to pi. By the way, if we were just doing like the top half of a sphere, I would go from 0 to pi over 2 because 0 is pointing straight up, and pi over 2 would be pointing like a right angle with the z-axis, and that would be right if we were doing the top half of a sphere, but we're doing the entire sphere, so I'm going to go all the way from pointing straight up to pointing straight down. For theta, theta just goes all the way around, and theta means the same thing as it does in polar coordinates. So the natural limits for theta are 0 and 2 pi. That means all the way around. Okay. I need to convert my function, and as we discussed, that's easy because I see rho squared right down there. So this is 1 over rho squared. And then I need to not forget the extra factor. the absolute value of the determinant of the Jacobian, but you don't need to remember all those words. You just need to know that it's rho squared sine phi, and I plan to tell you that. So there we go. It is fully set up. We just have to evaluate it. I see some things that cancel. And, okay. So I'm just rewriting it. We work our way from the inside out. I'm going to do an antiderivative with respect to rho. I don't see any rho, so I'm just going to stick a rho on there. That's the antiderivative. So we're there. Let me plug it in. When I put in 1, that's going to give me sine phi. When I put in 0, that's just 0. So I'm there. Now I am still working my way from the inside out. Antiderivative of sine phi is negative cosine phi. So I'm like that. Okay, cosine of pi is -1. And then I'm going to subtract negative. So I'm subtracting because that's just what you do when I'm plugging. I do plug in this minus plug in this. So that's this minus sign. The next minus sign is because of this minus sign. Cosine of 0 is 1. So after all that minusing, it looks like I've got a +1 +1, so I've just got 2. Antiderivative of 2 is 2 theta. Put in 2 pi, I get 4 pi. Put in 0, I get 0, so that doesn't do anything. So that's it. Okay, one more. This is what we have. So I plan to tell you what Green's theorem says, if you need to use Green's theorem. And the instructions are to use Green's theorem to evaluate this line integral, where C is the triangle with these vertices. And yeah, like I was saying, I will tell you what Green's theorem actually says. So here's what we're going to do. We are, of course, not going to, I mean, the whole point is we're not going to evaluate this line integral directly. We're going to evaluate this double integral, which is the same thing by Green's theorem. So let's start setting up the double integral. We apply Green's theorem. It's going to turn into the double integral, so I'm just copying this down. I'll worry about the region later. For right now, I'll just put an R down there. Let me do these partial derivatives. So F2 is the part with a dy on it. So F2 is negative x. So this is my F2. F1 is the part with a dx. So this is my F1. So what goes inside this double integral is the partial of F2 with respect to x, which is -1, minus the partial of F1 with respect to y, which is 1. So I've just got a -2 in there. Okay. But yeah, let's be more specific because we have a specific region to deal with here. We were talking about the triangle with these vertices. 0, -1, 1, 0, and 0, 1. So we are talking about this triangle. Okay, so now we get to have fun setting this up. I feel like I can go, here's what I'm thinking. I'm thinking y will go on the inside because I see y is going to go from, yeah, let me explain this slowly. If I'm thinking y is the inside, meaning dy is on the inside, dx is on the outside, my limits of integration for y are in general allowed to depend on x if y is on the inside. And I need to consider that because I think that's what's going to end up happening. And what I envision sort of like for an arbitrary value of x that might be somewhere in between 0 and 1, I imagine sort of shooting a line straight up. And what I want to keep track of is where do I enter my region and then when do I exit my region? And where I enter is going to be the curve whose equation goes here. That's my bottom limit for y. And then when I exit, and it's, yeah, when I say enter and exit, this is specifically if I'm coming from the bottom. So enter is at the bottom and exit is at the top. And so that's going to be this line. So let's just find the equation of these two lines. This is actually, let me do this quickly. This is a line with a slope of 1 because it goes over 1 up 1 and a y-intercept of -1. So I just use mx plus b there. This is a line with a slope of -1 and a y-intercept of +1. And so y is going to go from this to this. My limits of integration for x just have to be numbers that aren't allowed to depend on any variables. So I just look at the farthest left point has an x-coordinate of 0 and the farthest right point has an x-coordinate of 1. So there we go. It's set up. We just need to evaluate it. We go from the inside out as we do. So the antiderivative of -2 is -2y. So I plug in that and that. So -2 -x plus 1 minus -2 x minus 1. Right? Okay, so we get to, oh, there is just too much going on. I was thinking about doing that all in one step. So I'm just going to multiply this through, and then this turns into a plus, so plus 2x minus 2. Yeah, I was hoping everything would cancel, but unfortunately it didn't. 4x minus 4. Okay, not that bad. Integrate with respect to x. 2x squared minus 4x. 0 to 1. When I put in 1, I get 2 minus 4. And then when I put in 0, I'm going to get 0 everywhere. So this is all just negative 2. Great. Let me just say something real quick. Alternatively, at the very beginning, once I got to this point and realized that the inside is just a constant, it's just negative 2. You can pull the negative 2 all the way out, and then you just have a 1 inside. If you have a double integral with just a 1 inside, that means that it's the area of the region. So this is going to be negative 2 times the area of R. This region is a triangle, and the area of a triangle is 1/2 base times height. Let me turn the picture this way, because it's easier to look at this way. So the base is 2, because this goes from negative 1 to 1. So the base is 2, and the height is 1. So when I fill in the area of R, this is the area of a triangle once again, and the area of a triangle is 1/2. Base is 2, height is 1. So all that's just 1 inside of there. So we get we get negative 2. Same answer we got as before, just maybe a little bit less work. You can do it either way. Okay, I am tired, so I am going to upload these.